Hello, Nick here, M0NTV, and welcome back to my shack and to part 2 of our mini 3-part series on homebrewing a double balanced diode ring mixer. And thank you very much to everybody that watched part 1 and for the helpful comments as well that people made. Some really interesting stuff there and give me some things to think about actually for when I build the next one. I think I'll probably bear a few other things in mind, so thank you ever so much for that. That's really useful. And if you haven't watched the first one, the last video, then please go and have a look at that so you know what I'm talking about. But essentially I just built the mixer, but I didn't show any testing of it. All the testing is going to come in the next video, and we're going to put this mixer through its paces with or without other stuff and show you how to tweak it, and it's going to be quite a practical one. This time we're going to take just a little pause and a little kind of sidestep, if you like, to look at something that doesn't always get the kind of attention I think perhaps it deserves, which is the Diplexer. Now, what is a Diplexer? How do you build it? Why would you even want one? Are all very valid questions, and we're going to tackle all of those. So let's get stuck in. So we're going to do some diving deeper into the Diplexer, or as I like to rather irreverently refer to it, how to pimp up your IF port. Now, the first thing to tackle is why on earth would you even want a Diplexer? We'll get to precisely what it is and does in a minute, but we've got to take a step back first and think, well, why would we want to put anything on our IF port? What's the big deal? Well, the big deal is for a passive diode ring mixer, it's very important for the ports to be terminated in 50 ohms, but particularly the IF port. And that's the most important characteristic that we want to achieve for our IF port. Now, second I've got there, desirable is if we can perform some filtering as well. I mean, that's even better. But if we don't see a good 50 ohms impedance, that means that the SWR will be off, which means you'll get reflected signal, and then you'll get signal that will be reflected back into the mixer, and you'll get all kinds of spurious kind of intermodulation products and things, and it could be a right old mess. So really we want a good 50 ohms impedance on that IF port. And of course, if we can perform some filtering, even better, because we can filter out some of this stuff, because you know it's by the very nature of it being a mixer, it's a non-linear device, and these diode ring mixers, you know, you're going to get some harmonics and stuff. So that's a really good thing if we can do that. Now, the first one of these is by far and away the most important, so this is what we'll concentrate on. So how do we achieve a 50 ohms termination? And now this is where, in the immortal words of Charlie Morris, I am not an expert. Now if he has to say it, then I have to say it with bells on, right? And what follows is in no way any kind of proper scientific study or experiment, so please don't flame me over this. This is just me messing around, wondering what it looks like. Okay, so with that important caveat, there are different ways that we can try and ensure that the IF port on our mixer sees a 50 ohms termination. There are 4 here. I did try more actually, but these are just the 4 main ones that are tried and used. And so let me just describe what I did first of all. Right, so what I did to make this measurement is I started off, of course, with a double balanced mixer. Now this is not the one that I built in the last video, but it's identical. It's absolutely identical. So it's matched Schottky diodes, and there's the 2 transformers there. The only difference is I used the Dremel technique on this, so I didn't use the little pads that I glued up, but you can see it's just the same. Now, for this experiment, again, you know, whether it's right or wrong, this is just the way I did it. I left the RF port and the local oscillator port unterminated, right, just hanging. The IF port I connected, first of all, to my NanoVNA. Now, I'm not going to do a great thing about that. There's loads of stuff about the NanoVNA. It's a little bit confusing if you've got this is an old one, because the ports are marked channel 0 and channel 1, which makes no sense of the scattering parameters then, but I'm going to call them port 1 and port 2 because that's what they are, in fact. So port 1 measures, it puts out a signal, and then it measures how much of that signal is reflected back. So that's the basic setup. It's the IF port on the double balance mixer, connected to the NanoVNA, just on the port 1, getting the reflected signal back to see how close to 50 ohms we are. And then I inserted these other methods in between. So in between the NanoVNA and the IF ports, I put these other things to see whether that would help and how much in securing a better 50 ohms match. Right, so that's the setup. So what did I insert in between? Well, first of all, I did the most basic, which is a 51 ohms resistor. Now, in truth, I didn't actually insert this in between. What I did is I tacked it on from the BNC pin, from the live pin on the BNC connector to ground. Many people have used this technique. George Dobbs, God bless him, has used this. Charlie Morris has used this. And we'll have a look at the results in just a moment, but that's by far and away the simplest method, no question about it, because it's just soldering on one resistor to ground. The good thing about resistors is that they are frequency independent. In other words, they, you know, a 51 ohms resistor is a 51 ohms resistor no matter what the frequency of the signal you're putting through it. Whereas when you've got reactive components like inductors and capacitors, then things change depending on the frequency that goes through it. But you don't have that problem with a resistor. So then moving up from that simplest thing, I kind of went the next simplest solution, which was to use a pi attenuator. Now the one you can see down here on the left is just what I had in the drawer. So, I mean, you wouldn't choose to have a 6 dB pi attenuator, but the thing about a pi attenuator, and I'm sure you've seen them, it's essentially just 3 resistors. So it's 2 shunts to ground, and they're the same value, and then usually a lower value one in series between them. So it's just 3 resistors. But the great thing about it is you can design right from the get-go what the attenuation is, and actually you can design it to have a very, very low attenuation. In fact, just, you know, less than a decibel, actually, just fractions of a dB, and we'll look at the results of that in a moment. Thirdly is the bandpass filter. Now the reason I included this is that some of the comments that I got after the last video, I think somebody said at one stage, well, I wouldn't probably think about using a Diplexer, so I'd just stick a bandpass filter on the IF port. So I thought, well, yeah, let's try that and see if that, you know, makes a difference. And then finally, the Diplexer, and I appreciate I haven't told you what it is yet, and we're going to do all that in a while, but I wanted to show you first, before I explain the Diplexer, why I think it's worth looking at. So that we've got these 4 different approaches of doing it. So I did these tests, and what results did I get? Well, okay, here goes. So now what you're seeing here are some screen grabs from the NanoVNA Saver program, which enables you just to plug your NanoVNA via a USB cable into your computer and to see the results on the larger screen of your computer, which is great. Now what you're seeing here, the signal leaving from port 1 and being reflected back into port 1. So we're seeing the measure of reflected signal. So just think about this. So this is SWR, we know about this, we're hams, you know. If we had a perfect 50 ohms, we would have a 1-to-1 SWR. Now you'll see, top left, the IF port alone, about 2.3. So that is doing nothing. That's just plugging the NanoVNA into the IF port of the mixer. And it's pretty flat, but it's a bit high. So if you move along the top row then to the 51 ohm resistor, and you'll see, I mean, that's excellent. You get a great match with just one resistor. Moving across a bit further, the pi attenuator, again, is pretty good. Probably about 1.3 to 1 or something around there, and actually it actually drops down a little bit higher in frequency, interestingly. But again, yeah, not bad at all. The bandpass filter is an interesting one, because now just note the vertical scale on this one. The others have 1 to 3 as the SWR up the vertical scale. This goes 1 to 25, and that's because the SWR out of band is so horrific that the software had to recalibrate it and put a different scale at the side. So you'll notice that actually within the passband, this was a 17 meter, but it could be anything. Within the passband, actually it's not bad, the SWR, but out of the passband it's dreadful. So and that's what you've got to watch. And so for the people that say, well, I just stick a bandpass filter on it, well, that's all right. That answers one of your things about doing some filtering. That's great. But there is a danger with such a high SWR. If any other frequencies make it through, they're just going to get reflected straight back. And then you're going to have all kinds of stuff going on in your mixer that you don't want. And finally is the Diplexer. And you'll see the Diplexer has... there is a little peak there. Again, we're back to the lower scale now, so don't compare this to the bandpass filter. Compare it to the other ones. But even at the peak, it's just over 1.67, isn't it, to 1. But the rest of it is pretty flat throughout. Now let's have a little look at what this actually means, because all I've been showing you has been how good a 50 ohms match we get and over what kind of bandwidth. But that's not the only consideration that we've got. So if we take the first one, the 51 ohm resistor, the simplest one, yes, it's a good match. Yes, it's a wideband impedance match, but it is lossy. Now I did some calculations with the help of LTSpice actually about for my particular mixer what the losses were, and I calculated that by putting that 51 ohm resistor on the IF port, I got an additional loss of nearly 4.5 dB. So it is quite lossy, and of course, you know, it's a resistor. You don't get any filtering. So, but it meets the first two criteria pretty well. So, kind of moving up to number 2, the pi attenuator. Again, good 50 ohms match. It's a wideband match. It's got what I would call designed loss. That is to say, it's up to you. The first one with the resistor, who knows what the losses are going to be. The good thing about the pi attenuator is that it's a more calculated thing. So you design it with a certain amount of attenuation, and as I've said before, you can make that level of attenuation very, very low, and certainly lower than the 4.5 dB that I got just with my 51 ohm resistor. So you could have the benefits of the first one, but with less loss. And pi attenuators are great anyway. I mean, I use them extensively in all my transceivers, usually either before or after amplifiers. But of course, you don't get any filtering because It's just 3 resistors. So then we move on to the bandpass filter. I'll start halfway down actually here, because it is low loss if you build it carefully. Yes, of course, by the very nature you get some bandpass filtering for the first time, so you can filter out some of those harmonics and other intermodulation stuff that you might have. It has got a pretty good 50 ohms match, but crucially it's very narrow band, so that match is only as good as the bandwidth of your filter. Outside it, it's horrific. So and that, I think if you were just using that, that might not be that good, because I think you'd probably have to use number 1 or number 2 as well as that if you wanted to secure a 50 ohms match, because on its own it'll do the filtering, but you know, it won't give you that wideband match. And fourthly, the diplexer. And I know I haven't told you much about it. We're going to get to that first, but let me tell you, what it will give you is a good 50 ohm match. It's a wideband match. It's very low loss. I think mine was 1.7 dBs insertion loss, and actually, you know, if you build it carefully, you could probably get it lower than that. And it does bandpass filtering. So actually, I'd like to suggest that it does what all the others do. So it gets a good tick by all these, but without the negatives of some of the others. So I think it's at least worthy to be considered if you've never thought about building a diplexer on your IF port. So what is a diplexer? That's a pretty good question, and it's about time we answered it. Well, a diplexer is essentially a 3-port device, and what a diplexer will do is it will take one frequency and will send it to one port, and it will take another frequency and send it to another port automatically without any intervention from you. It's this ability that a diplexer has to send a signal of a particular frequency over here and a signal of a different frequency, or in our case everything else, over here, right? And that's what a diplexer does. It separates these, or you can use it in reverse and combine them, but for our needs that's what it is. So let's have a look at the schematic and I'll show you how it works. So at long last, here is our diplexer schematic. Now this is an LTSpice simulation, so you can ignore the signal source bit here. We imagine that's just the input port here, and ignore the load here. So this is the kind of output port here. Now, those of you that were paying attention will say, didn't I say it was a 3-port device? Yes, it is. So this is the input. This is one of the outputs, and the other output port, it's probably not immediately obvious, is down here. It's just that in this case, this second output port, we're sending it just to ground, but we could send it somewhere else if we wished. But that's just the nature of what we're trying to do here. So and it's bidirectional, so you could reverse this and send a signal in here and have the output ports here and here. So what's it actually consisting of then? Well, just take a closer look at this, because what you've got here is a series tuned circuit, a capacitor and an inductor. And a series tuned circuit, sometimes called an acceptor circuit, is a bandpass filter. So what that means is this at resonance, and this is tuned for resonance at our intermediate frequency, 13.3. So at 13.3 megahertz, there will be a signal coming through here. We'll see a very low impedance, and which is what we want. So at 13.3 megahertz, the signal will come through here, see a low impedance, pass all the way through and out into the rest of our radio. Ideal. That's just what we want. But if we look down here, this is a parallel tuned circuit. It's a tank circuit. Anybody that's ever made a crystal set will recognise it. You'd put an antenna up here and a diode here and a resistor and your crystal headphones here, and that's it. And it functions exactly the same way. So this is what's called a rejector circuit or a band stop filter. And that's because it does the opposite of the series tuned filter. So here, this sees a low impedance at the point of resonance. This sees a very high impedance at the point of resonance. So, so what that means is, let's imagine we've got our 13.3 megahertz signal coming along again. It's going to see a low impedance here. You might think, well, why doesn't it go down here? Well, because down here, it's going to see a 51 ohms resistance, and then it's going to see a very, very high impedance here. So that will be a huge impedance, much higher than the impedance it will see here. So basically, RF is lazy. It won't make it hard for itself. It will take the path of least resistance and will travel through here. And so the bulk of your signal will go through relatively unattenuated at your desired frequency. Now let's say we've got a signal which is not at RIF frequency. It doesn't matter what it is, anything that's not 13.3 megahertz. It will come here, it will see a very high impedance here, so it won't be flowing through in the way that the 13.3 megahertz signal did. But down here, this tank circuit, this parallel tuned circuit, will give a very low impedance to everything else that's not the frequency we want. So all it will see is a 51 ohm resistance from that resistor, and then a very low impedance to ground, which will be much less than this. So what that means is that our chosen frequency, our IF frequency, the signal will pass through relatively unattenuated, but everything else will see a high impedance here and we'll see a much lower impedance here. But it will all pass through this 51 ohms resistor and then go to ground. So that's how we ensure we've got that consistent resistive 50 ohms termination across such a wide bandwidth. Clever stuff. And the reason we've got a 51 ohms resistor here, of course, is because it's bidirectional. So if you were to reverse it and send the signal in this end and take the signal out that end, it would just go through this 51 ohms resistor and through that way. So really, it's two filters in one. Way! Everyone knows I love a filter. Get two for the price of one with this, but very, very clever. Combining a band pass and a band stop filter to make sure not only that you pass the signal that you want, but that everything else gets grounded and sees a 50 ohms termination. Now, in terms of building this thing, and I'll show you the one I made in just a moment, but it's interesting, you'll notice 5.98 microhenry, so that's quite a large inductance, not difficult to make. So I use, as I've indicated here, a T56, a yellow toroid, and put on 38 turns of 28 gauge wire on that. Then I used a higher quality trimmer capacitor here. You've got a high amount of inductance and a low amount of capacitance, and the parallel is the opposite. That's a high amount of capacitance with a low amount of inductance. But what will help you to steer that frequency into just the right place, because it's very difficult to build something to this specification precisely. So it's great if you can have a bit of variability, and actually you want the variability in the series circuit here. You want to be able to adjust that capacitance, because just fractionally adjusting that will change where your resonant frequency is. So that's good, and that's fairly easy. Just have a variable capacitor there, a little trimmer. Now, when it comes to the parallel tuned circuit, it's not quite so easy. I mean, that's all right. I just used two fairly high capacitors in parallel with one another and could get something fairly close to that. That's not a problem. The issue is L2, because actually it's really a very low amount of inductance, and this is the one you want to be variable. Now, you can buy shielded variable inductors, and I bought a few that are canned, but actually in the end I went back to doing what I've done in previous diplexers that I've built, which is just to homebrew my own, which is to take a smaller core type 6 toroid, a T37 6, and just use literally 3 turns. And you can make it variable. Anybody who's ever wound a few toroids will know if you stretch the toroids out a bit more on the core, you'll reduce the inductance, and if you bunch them up a bit, the turns, you'll increase it. So yeah, that's it. And let's have a look at the finished article. And here is my Diplexer. Now, ignore the familiar mixer behind, but it's the bit in the front that we're looking at. And you can probably just see there the big toroid, which is part of the series tuned circuit with the variable capacitor. That's the series bit. And then at the front on the right hand side, you'll see the two green capacitors going to ground, and the other smaller yellow toroid, that's my smaller amount of inductance, which is going to ground, and then the 251 ohm resistors as well, which connect both those bits to the input and the output. Now what I did for the larger inductor, I actually coated it fairly liberally with some of that nail varnish sealer stuff, the clear polished. My wife kindly donated some of that and it just holds the turns in place a lot more. So once you've got it where you want it, you don't want the turns all moving around and messing up your inductance. So that's good, you can do that. And then in terms of sealing them to the board, just to hold them in place so they don't rattle around, I used a bit of that Bondic stuff, that UV welding stuff. I don't know whether you've come across that, but it looks a bit like, you get like this pen, and it's like a clear kind of glue, and you kind of blob a bit down, and then you put the top on the pen, you turn it around, the other end is a UV light, and you cure it with this UV light for just a couple of seconds, and it sets immediately, and it's amazing stuff. So a little goes a long way. So yeah, so I tend to use that just to kind of hold them in place. Doesn't need a lot, but yeah, that's very good. So yeah, so that is the Diplexer. I suppose the question now is, how did it perform? Because what I did is I put on again the trusty NanoVNA, but this time I ran it with both ports with a what they call a 2-1 measurement. So you have the same signal coming out as we always have done from port 1, but then we're measuring what we get back on port 2, and the NanoVNA calculates how what left on port 1 is different to what it receives on port 2. And this device under test, our Diplexer, will be in between those ports, you see. So we'll be able to see the difference that the Diplexer actually makes. And that's what I'll show you now. So how did my Diplexer fare in the tests? Well, this is a screen grab of the whole of the screen of the NanoVNA Saver. And the great thing about that particular piece of software is that you can actually do more and see more than you can on the device itself, because you can do different tests at the same time, which is really helpful. So just to point out, I've got 3 markers here. The red marker is the IF frequency of 13.5. It's the closest I could get to this. The green marker is the RF frequency of 18 megahertz, and the blue marker is the local oscillator at 31.5. So if you just notice, all I'm going to say about the Smith chart is notice all those markers are bundled up together. That's always a good sign on that particular point there, because that's going to show that they're all seeing a similar 50 ohms impedance. We'll come back to that in a minute. Top right, S21 gain. So this is the filtering action of our Diplexer, and you will see, if I look on the left hand side at the top here on the data, here we are, S21 gain minus 1.708 dB. So that's your insertion loss, 1.7. So really good actually. And you can see how if I did have any of these other frequencies coming through, how they would be attenuated. So the green RF frequency is at least 15 dBs below my IF, and the local oscillator is about 26 dBs around about there below my IF as well. So it performs that filtering action very well, and that will certainly help in cutting out some other of the mixing products. If we go bottom left, we're back to an S11 now. So this is the reflected signal again, just like the test that I did before. And you'll see just how good the Diplexer is now. I mean, just take a look at that SWR. I mean, the highest it rises to on this particular sweep at 51 megahertz is less than 1.2 to 1. And actually, where our main signal hopefully will be going through at the IF frequency, the little red dot there, we actually see here it's 1.026 to 1, so really very good indeed. So we're seeing a very good 50 ohms termination across there. And to see that in a bit more detail on the bottom right, so this is a measure of the impedance, and here we're seeing 50 ohms on the bottom and 60 ohms on the top, so it's not a huge range. And even there we can see that the worst it gets to on this particular sweep at 51 megahertz is 54.5 ohms. So it's pretty good really, and I think you'll see why I rate Diplexers, and although they are a bit more fiddly to do, certainly a lot more fiddly than just soldering in a 51 ohm resistor, but in many ways you kind of get the best of both worlds. You get a good filtering action, but you also get a very good wideband 50 ohms termination. So there you have it, and I just really wanted to explain why I think Diplexers are worthy of consideration. You don't have to build one. As I said, you can just solder a 51 ohm resistor if you wish, but I think they have some good advantages if you can be bothered to to build one. And now the real proof of the pudding will be, of course, is when all this is connected up together. We know the Diplexer works, but that's coming in the next video, I promise, right? So I'm going to present a few ideas there, but that's coming up in the next one. That's all for now. Thanks very much for watching. If you've got any comments or questions, then by all means feel free to leave them. But until the next time, look after yourselves, stay safe, bye-bye.